Good afternoon, everyone. My name is Tarun. I'm a PhD student at OSU Tulsa, currently working under Dr. Raman Singh. Today, I'm going to talk about how to quantify alignment of graphene nanoplatelets using AC conductivity measurements as an in situ technique. Before I talk about alignment, I want to talk about the structure of graphene nanoplatelet and why is it favorable for alignment. Graphene is a hexagonal 2D atomic crystal, as you can see in this picture. So one single layer of graphene is called monolayer graphene, but graphene tends to stack up and which are held by van der Waals bonds. So the thickness of graphene nanoplatelet is around 5 to 50 nanometers, but the length of the graphene nanoplatelet is around 25 microns. Due to the significant difference, it gives rise to an aspect ratio of 3000 to 5000, which makes it suitable for alignment. Physically, the graphene comes in the form of black powder. So there are many applications that involve graphene nanoplatelets, but the primary ones are in structural reinforcement in composite materials due to their lightweight to strength ratio. Apart from that, due to the high electrical properties, they are used in power storage in batteries and supercapacitors. And they're also used as lightning strike protection and solar cells and as well as lubricants. One interesting thing to note is that the properties of single graphene nanoplatelet differ in both parallel and perpendicular direction. In parallel to the surface, the properties are significantly higher, as you can see in this table. The main properties that we'll really focus are electrical conductivity, tensile strength, and thermal conductivity. So electrical conductivity is almost 10 power 7, like 5 orders of difference magnitude. The major drawback of using graphene nanoplatelets is their natural tendency to agglomerate. So in figure 3, you can see separately spaced graphene nanoplatelets that tend to agglomerate because of van der Waals forces, forming a lump of particles. So these lump of particles are not as effective as single graphene nanoplatelets, which provokes the use of higher amounts of GNP to obtain suitable properties. But this ultimately it gives rise to dispersion problems in epoxy and also causes some negative effects. One of the reasonable solutions to remove agglomeration of graphene nanoplatelets is alignment. So alignment of graphene nanoplatelets will not only utilize the directional properties but also retains the surface area of graphene nanoplatelets and also decreases the electrical percolation threshold where it is suitable for electrical properties or applications. So the structure of graphene nanoplatelet is oblate spheroid as seen in figure 4, which makes it very suitable for alignment in parallel direction. To align GNPs, we created an experimental setup that can pass alternating current between two aluminum plates separated by polymer spaces to prevent shorting. These are connected in series with a digital multimeter, an amplifier, and an AC signal generator. The schematic is shown in figure 6. So these are the aluminum plates, and in between there's graphene nanoplatelets, which is connected to the digital multimeter, which is going to acquire data through LabVIEW software for AC conductivity, and it is connected to a power amplifier which is connected to AC signal generator, which provides the AC signal. And so basically the materials are epoxy, hardener, and graphene. The graphene and epoxy are mechanically stirred for 60 degrees in an hour, and the mixture is passed through 3-roll mill where they break the agglomerates, and hardener is added in a stoichiometric ratio, and the aluminum then the mixture is poured into aluminum mold and electric field is applied for a set amount of time. So to figure out the amount of time required for alignment, it is important to understand what exactly happens to a graphene nanoplatelet when it's experiencing an electric field E. So when it's experiencing alternating electric field, the graphene nanoplatelet causes a dipole moment and the charge separation happens like plus Q and minus Q along the extremities of this particle. These particles tend to attract towards the electric field in this direction. These forces will create a torque around the center of the particle, and it causes the particle to rotate. And this particle is opposed by the viscous torque of the epoxy. So there are many factors that affect these alignment process, which are electric field intensity, viscosity of the mixture, and graphene weight percentage. So the time required for rotation from initial angle theta I to final angle theta F was calculated by Wu in 2015. After the particles are aligned, they tend to attract towards each other because of the charge formation plus Q and minus Q. So as time passes by, these two particles come closer together and form chains as shown in figure 8. So Wu also found a formulation which tells us about the distance between two particles and the time it takes to achieve the chain formation. The major drawback of this present model is that it assumes a constant viscosity for any GNP concentration in epoxy, which is practically not true because as you keep adding graphene nanoplatelets to epoxy, the viscosity keeps increasing and it's a significant factor to be considered for alignment. So to update this model, we included the Gamble's method for calculating the viscosity of a polymer mixture um, for different weight fractions which are substituted in the formula. So adding all these up, we end up with analytical results for the modified model. So in this picture, you can see the time required for a single graphene nanoplatelet um, to align from 0 degrees to 90 degrees for three different weight fractions. So these results are based on the formulas which you saw earlier. So similarly, the translation time is also depicted in figure 9 part B, where yellow is 2.8 weight% and red is 1.4 and blue is 0.7. Let's look at some of the experimental results. In figure 10, you can see the AC conductivity variation for three different weight fractions as the alignment process is taking place. Initially, at time t equal to 0, each sample has a limited amount of conductivity present, and as time passes by, they tend to get aligned and formation of chains take place as seen in this picture before alignment and after alignment, and the conductivity increases and it plateaus. So the approximate time for alignment is figured out based on the amount of time it takes for it to plateau. So comparing it with model results, we get reasonably well comparison, which also validates the model that viscosity is an important factor for alignment. Let's look at some of the results for DC conductivity measurements. So these experiments are performed after the sample becomes cured and it is hard. So in figure 11, um, it talks about the variation of DC conductivity for different weight fractions of 0.7, 1.4, for 2.8, for different aligned samples and randomly dispersed samples. So from normal and aligned samples, you can see a twofold increase in electrical conductivity just because of alignment is taking place. So we can also calculate the percolation threshold of composite. It basically tells us the minimum amount of particles required to make the insulating polymer conductive polymer. So for aligned samples, it was 0.4 weight%. For normal samples, it was 1 weight%. So a less weight of graphene is required to achieve electrical percolation threshold. And we also not only it increases the electrical properties, but also it increases the strength in aligned direction. Table 4 talks about the increase in Young's modulus in aligned direction. We saw a 9 to 15% increase in Young's modulus because of chain formation and alignment. To conclude, we successfully aligned graphene nanoplatelets in epoxy, and an in situ characterization technique was established which could quantify the alignment process. We also achieved twofold increase in DC conductivity and a percolation threshold of 0.4 weight%. So the future work is to capture the AC conductivity by an analytical model and extend this to graphene oxide for application of supercapacitors. Thank you.